I have the same reminders today as I did on Tuesday. There's homework 5 that's due on um, April 22nd. As of now, we've completed everything that you need for all the required parts of the homework. So you'll be implementing SVM, you'll be deriving logistic regression, implementing it. And this would be a good exercise to compare these two algorithms. And there's an extra credit question involving neural networks for all practical purposes, you'll have the content for today. Um, a side effect of this homework is that you'll have 2 new learning algorithms implemented on your own, which means you can also, as you're running them on this data, you can also run them on the project data. And that'll give you 2 more things that you can submit for your project. You need 3 more um, for the final project, which is due also on April 22. Um, and you'll have to make submissions on both Canvas and Kaggle by that day. And there's also a final exam scheduled that week on the 25th, which should be the Friday at 10:30. And it covers everything that we did, including and after computational learning theory. It'll have a similar flavor as your midterm, so you don't have to worry. Any questions? Yes.
This is a technical question regarding logistic regression.
Okay.
You said that it is an algorithm that we can use, but correct me if I'm wrong here. As far as I'm understanding, logistic regression is about predicting probabilities
That's
of
right.
things, aka it's
Yes.
continuous.
Yes.
So how could it then be applied to our classification problem?
Because logistic regression predicts the probability that the label is 1. So it predicts probability that the label is 1 given an example and whatever parameters that you have. But suppose you've trained the model. Now, given a new example, you can ask, what's the probability that the label is 1? You get this. And if that is more than a half, then you predict label is 1.
Okay.
Otherwise, you predict the labels the other thing. For your project, I don't know if it was -1 or
I think it's 0.
0. So then let's call it a 0. So yeah, that's pretty much it. And we kind of covered this in the last lecture because you could do this, but remember, doing that is equivalent to saying, so I'll just do the +1 part. That condition is the same as saying 1 over 1 plus e power minus w transpose x is greater than or equal to half. So the label is 1 when that quantity is more than half. That's the sigmoid, right? But that's exactly the same as saying 1 plus e power minus w transpose x is less than or equal to 2. I've just inverted these things. But that's exactly the same as saying minus w transpose x is less than or equal to 1. I can take log on both sides, which means minus w transpose x is less than or equal to log 1, which is 0. But I can negate both sides, which is equivalent to changing the sign of the inequality. W transpose x is greater than or equal to 0. So the label is 1 if the dot product of the weights and the features is greater than or equal to 0. So the decision rule is exactly the same as in SVM and perceptron. And that also reminds me, one thing that's not explicit in the slides, but something that you need to always keep in mind is there's a bias term, which is not shown here. It's always W transpose X plus B. And if you do not want to have a plus B, then you should add a bias feature. For your implementation, I would recommend adding a bias feature because then you can just literally implement this and you're done. But see, the thing is, yes, if you want to predict probabilities, you can use the probability to predict the label is 1 using this criterion. Or you can just use the weights and see if the dot product of the weights and the features is positive. So the label is nothing but the sign of W transpose X plus B. Does that clarify things?
Yeah.
Right. There is a question on Zoom, for the homework, can we initialize the weight vector and bias by adding random numbers like we did for the perceptron, or do we need to initialize them as 0? I believe in your homework, the initialization, the auto grader initializes it to random numbers. Oliver, the auto grader initializes randomly, right?
Students initialize their own.
Oh, so you initialize your own weights. Oh, the auto grader internally, the grading part, I think our official trial run initialized randomly. But here's the thing. For logistic regression, for SVM, and for perceptron, you are minimizing a certain function. Turns out that function is convex, which means the initialization does not really matter much. If you initialize to 0 or you initialize to random numbers, you should essentially converge to basically the same decision rule. There might be tiny differences because maybe it changes how long you need to run to converge, but it should not change the result drastically. So you can use either strategy for the sake of reproducibility. I would say just initialize to 0, and that way you get the same result the next time you run it. Even otherwise, you can get reproducible results by setting the random seed. But I would say I would encourage you to initialize to 0 just so that it's a reproducible result. Other questions?
So this formula, right, what if the distribution of probabilities very close to 1 over half, also 1 over 2? They don't mean that it's not very confident predicting.
That's one interpretation. That's an interpretation of this probability. That if the probability is very close to half, that means the model is not confident about this particular thing. You should be careful with that interpretation, because for that interpretation to work, this must be a valid probability, and there's a certain issue with that assumption. I'm not going to get into the details, but there's something called probability calibration, which you should look up. And these numbers that these models produce are sometimes not calibrated. So it does not express true uncertainty, but you can interpret it that way. In fact, there's a nice analogy between the probability interpretation and this dot product interpretation. If the probability is very close to half, that is equivalent to saying this dot product is very close to 0. It's just slightly positive if it's more than half, because you can work it through. Which means if the probability according to the model is very close to half, then your W transpose X will be very close to 0, which means the point will be very close to the hyperplane. So in some sense, the distance from the hyperplane behaves like a confidence. And the probability is really a normalized version of that distance. That's the other sort of you can either interpret it from the probability point of view or purely from the linear algebra geometry point of view. So from this perspective, it's close to the hyperplane. From the above perspective, it is most uncertain. Okay, the other set of announcements I wanted to make was not an announcement as much as just a quick discussion on what I expect from your final project submissions by the 22nd. There's also a late day, so you can technically go to 23, but I think your Kaggle submissions close on the 22nd, and Kaggle does not allow extensions on that, so it does not even allow late stuff. So this information is all on Canvas. I just want to go through this. You need to submit, you need to have 6 official submissions. You could have more than 6. If you have more than 6, I encourage you to mark out which 6 of them are your official submissions. Help us, it'll help us grade better. It'll help us with the grading when we kind of go through your submissions and figure out which ones we should consider. Maybe you could even mention them in the report if there's room.
So related to that, I think you can like name your submissions.
Yes.
In Kaggle, like please name them like decision tree with this feature transformation
Yeah.
or whatever, like it'll save us a lot of time.
It'll save us a lot of time if you use the name, if you give a meaningful name so that we can actually trace that to your report. So you can even say, put the word official in the name. That will help us. If you have 500 submissions on Kaggle and you want us to hunt for 6 of them, it's going to be a little bit tedious. I appreciate if you have 500 submissions, but also it's going to slow things down. So, oh, there's a question on Zoom. I'll come to that right after this discussion. So, name the submissions. Yes.
In Kaggle, you can select the 6 you want.
Yes.
So that be sufficient.
Yeah, as long as it makes it very clear which of them is official, but name them, please, because even after you submit them, even if you select 6 of them, I don't want it to be submission 1, submission 2, etc. It would be good to know submission 1 is actually decision tree, and so on. So give it descriptive names. And your report, don't make it more than 6 pages. I just need to know what the high level, your perspective, your overview of the project, what ideas you explored, what you learned from doing this process, and what ideas from the class did you use, what ideas from outside the class you brought in, any discussion of the results, any interpretations of the results. For example, if your data is linearly separable, if not, what's going on? What do you think is going on? Can you kind of, one of the things about machine learning is it's remarkably easy. In the sense that you just throw data at an algorithm, you get some numbers. But the numbers by themselves are only half the story. Interpreting those results is actually useful. Understanding why this model worked and why this did not. What could you guess about the underlying, the nature of the problem from what you observe? From what you observe and what you know about the task. It's a useful sort of a descriptive exercise, and it would be good to kind of spend a little bit of time on that. And one thing I always ask for my project reports is, if you have more time on the project, what else might you want to try? And often I look forward to reading that part of the report because it tends to be an open-ended exploration of ideas. And also submit your code on Canvas. There's a lot more instructions on the code in the Kaggle part of things. So on Canvas. So take a look at that. Any questions about the project?
When we submit our code, do we need to like group different submissions into different folders?
Yes. Most importantly, have a README file that tells us how to run your code and where your different submissions are. Just have a text file with readme.txt inside the submission, inside your directory. Don't include the data inside your code submission because I think Canvas will get very angry with me because I think there are some file size restrictions. So just the code. Yeah.
Do we just need to go for like, if we created like a decision tree, do we just need the decision tree code, or should we also put like cross-validation for that?
Why not submit the cross-validation part? I mean, I'm just curious.
That's like perceptron. Cross-validation.
Yeah, submit it. Why not? Yeah. And you can just tell us how to run these things. We're not going to run everything. We'll run, on demand, I would say. Okay. There's a question on Zoom. Going back to this discussion here, what's the difference between these two perspectives? If they end up being the same thing, why are these useful? And why might one be more helpful than the other? Honestly, they are isomorphic to each other. Any conclusion that you might arrive with the probability perspective from this point of view, you can arrive from this point of view. But it's not what conclusions you arrive with this, but it's what else you do with this that could be helpful. So if, for example, you use SVM or perceptron, you get a weight vector. And you can ask, is this model confident on this example? And to answer that question, these two algorithms don't natively are not trained to be probabilistic. You can always take the weight vector of the SVM, apply the dot product, squeeze it through the sigmoid, and get something that's a number between 0 and 1. You can say that number is the probability. But in fact, that's not going to work too well because SVM, if you remember, is trained to put examples away from the margin. It's the training process forces this separation, which means you will quite likely not get too many points that are close. So the margin / distance from the hyperplane interpretation might be more helpful in that world. For logistic regression, because it's natively probabilistic, the probability interpretation might be more reliable, more sound, because by design, the sigmoid is meant to be the probability. But it just so happens that these two interpretations can be transferred from one to the other. What might be actually even more helpful is sometimes you might want to take this probability and do something. You have multiple classifiers that are interacting with each other, and you want to combine their probabilities to make a consensus decision somehow. Multiple classifiers, maybe for different tasks. And then the probabilities start becoming useful because you have the tools of probability theory to help you compose things in interesting ways. Maybe you want to interpret the high dimensional space of features using this linear classifier, and maybe you want to think about polygons or polytopes inside that high dimensional space. And then the linear, the geometric perspective becomes useful. Depending on what you want to do, these two perspectives end up offering slightly different insights, and more importantly, they open up slightly different sets of tools that you can pursue. And it's useful to have both interpretations because depending on what you want to do, you could use a different toolkit. I hope that kind of somewhat gives you a sense of the answer to your question, Jared. I'm going to now actually get into the actual content of today's lecture, which is, we were talking about logistic regression in the last lecture, and I want to wrap that up just a little bit, which is by talking about loss minimization. For logistic regression, we talked about this particular loss. There is a loss, there's what looks like a regularizer, what looks like a loss, but really we derived this using maximum a posteriori learning. I want to connect this back a little bit more, once again, to loss minimization. Just to remind you, we've seen this before, and this is just a quick reminder. In this setting, your examples are drawn from some distribution, possibly unknown, and your oracle function labels those examples, and you get a hypothesis. You get labeled data set, and you want to find a hypothesis H that mimics the oracle. And in a perfect world, what you might want to do is you might want to minimize this loss L, which penalizes H for whatever predictions it makes. The loss is a function that takes the ground truth and the prediction. Sorry, this thing is the prediction, this is the ground truth. And in an ideal world, you want to minimize the expected loss, but unfortunately, you can't possibly compute an expectation over this distribution that's unknown. Instead, we minimize the empirical loss on the training set. We've seen this before. Hopefully, this seems familiar. But minimizing the empirical loss by itself is a problem because you can overfit, and you need something that guides the learner towards hypotheses that avoid overfitting. One sort of an idea to avoid overfitting is to use simpler hypotheses. In other words, you can penalize complexity, and you can do that by using something called a regularizer. There are other ways to penalize there are other ways to avoid overfitting, and we're going to see one of those very soon, maybe next week, quite likely, actually next week for sure. But so far, what we have seen is this idea of regularized uh, loss minimization, where you're augmenting this optimization problem by including a regularizer. For a linear classifier, a common kind of a regularizer is this the norm of the weight vector. Sometimes it's also called the L2 regularizer. So you have the optimization problem is minimize the sum of this L2 regularizer plus the loss over the data set, and there's this term C that mediates these two things. Once again, we've seen all of this before. We've seen multiple different kinds of loss. We've seen the perceptron loss, we've seen the hinge loss, we've seen the logistic loss. All these losses penalize mistakes. But in a perfect world, if mistakes are all you care about, then why not just why all these strange losses that penalize mistakes in these different ways? Why not just count the number of mistakes? For every hypothesis, you count the number of mistakes it makes on the training set, or take the average number of mistakes on the training set, add a regularizer, and find the hypothesis that minimizes it. That could also be a loss function. That loss is the 0-1 loss. The 0-1 loss simply takes the ground truth and the prediction, these two things, and it takes away 1 point if there's a mistake. If the ground truth and the prediction don't match, otherwise it takes away no points. That's a reasonable loss. That's a reasonable penalty. Except that the 0-1 loss is intractable. We also know that for a linear classifier, you can write this expression that there's a mistake as I see that I have, yeah, if Y is the ground truth and W transpose X is the prediction for a linear classifier, this quantity is negative for a mistake, which means the 0-1 loss for a linear classifier is 1 when YW transpose X is negative, and it's 0 otherwise. So far, so good. I've done this before, so I don't want to dwell on this unless there are questions. The important point here is that YW transpose X shows up. YW transpose X shows up in perceptron, it shows up in logistic regression, it shows up in SVM. So we can actually plot the losses as a function of YW transpose X. There are many different loss functions that exist. We've seen the perceptron, SVM, logistic regression. It turns out AdaBoost also minimizes a loss called the exponential loss if all your features are the weak learners. And different loss functions, all of them involve this YW transpose X. So let's look at plots of these different loss functions. So I'm not plotting AdaBoost because the exponential function kind of just grows a little too fast. In all of these cases, the horizontal axis is YW transpose X, and the vertical axis is the loss. The perfect, in an ideal world, we would like to minimize the 0-1 loss. The 0-1 loss imposes no penalty if YW transpose X is more than 0, and it imposes a penalty of 1 if YW transpose X is less than 0. Very obviously, this is not even a continuous function. So it's, for many reasons, this is a complicated function to optimize. So we have surrogates. One of the first surrogates we saw, though we did not actually see it in this form, was the perceptron. The perceptron loss is 0 when YW transpose X is positive, and it increases as YW transpose X gets more and more and more negative, which means there is a notion of a worse mistake. Being, if YW transpose X is here, it's much worse than YW transpose X being here, because the loss is so much more. As an exercise, you should take this exact function, the perceptron loss, compute its subderivative, plug it into the stochastic gradient descent formalism, and you should be able to recover the batch perceptron orbital. Another surrogate is the SVM. SVM and perceptron look awfully similar to each other. Both of them have this sort of a ramp going up. The only difference is perceptron, the ramp starts at 0. For this SVM, it starts at 1. And in the loss expression, that's because SVM has a 1 minus YW transpose X. Essentially, SVM introduces this margin here. It's not enough to be for YW transpose X to be positive for there to be no loss. YW transpose X has to be more than 1 for there to be no loss. Logistic regression, you can plot the logistic loss and it looks something like this. It imposes a small amount of loss even when YW transpose X is positive, but it grows quite drastically after on the negative side of things. Just another loss function. It's another surrogate for the 0, 1 loss. Now, one question that students often ask me around this point is, which one should I use? Which of these is the right algorithm to use? And to answer that question, I want to take this exact plot and zoom out a bit. When you zoom out a bit, you see that all of them on this side have very, very low loss. And on this side, they have increasing loss, and it gets more and more as you get as you get further away from 0. You can zoom out even more. And frankly speaking, they are essentially imposing the same preference, right? So the fact is, a well-tuned SVM, by tuned I mean with hyperparameter selection done the right way. A well-tuned logistic regression, again, proper hyperparameter selection with learning rates and the sigma that shows up in logistic regression, or sigma square, really. And a well-tuned perceptron with averaging essentially should behave very, very similarly to each other. There are 3 different learning algorithms that learn the same hypothesis space. They impose 3 different preferences over the hypothesis space, but because the losses essentially look very similar at an aggregate level, these 3 algorithms should perform somewhat similarly to each other, provided you do your hyperparameter selection well enough. There is a small amount of, there's some nuance there. For SVM and perceptron, SVM and logistic regression, you can use the algorithm as it is because the regularizer promises generalization. For SVM, the regularizer prevents overfitting because of the prior for logistic regression. It promises generalization there also. For perceptron, there's no regularizer. So how does generalization come in? You can't do it as it is. You need to have averaging. There was a period of time when people were even entertaining the possibility of averaging for SVM and such things, but people don't do that anymore.